Well, we introduced the word wire. Now, for most of the problems that we're going to do, we're going to be working with an ideal wire. So an ideal wire is a wire such that there is no resistance to the flow of charge. So if there's no electrical resistance, there's a few properties that we should be aware of. Before we discuss those properties, the typical symbol we use to represent this wire, this ideal wire, is just a line. Now, in actuality, this wire has a size and a shape and a length. But the symbol that we're going to use when we're representing an ideal wire in a circuit is just a simple line. Now, the thing about ideal wires is we could consider that they're all identical. And what do we mean by that? Well, it means that an ideal wire can be of any length. The length of an ideal wire doesn't matter because it doesn't change its properties. An ideal wire can be of any thickness without changing its fundamental properties. An ideal wire can be in any shape without changing its fundamental properties. Now, this gives us a lot of flexibility when we're drawing circuit diagrams. So a circuit diagram might have a funky connection, a funky setup of wiring. However, we could just simply replace any set of ideal wires with just straight line segments that might be easier to work with and easier to understand. So some very important properties of ideal wires. The potential at all points in a single ideal wire is constant. In other words, there is no potential difference between 2 points in an ideal wire. So let's take an ideal wire. I'm going to give it a size and a shape just for illustration purposes. But again, remember, we could just use a simple line. Now, this ideal wire, we said that the value of electric potential is the same at all points in this wire. So let's say we have a measuring device that allows us to measure the potential difference between 2 points. We will call this measuring device a voltmeter. And this voltmeter allows us to measure a difference in potential between 2 points. Let's call this point on the left point A, and let's call this point on the right point B. So point A in the wire would have a potential associated with it, which I'll indicate as V sub A. And point B in the wire has a potential associated with it, which I'll call V sub B. Well, if this is an ideal wire, V sub B minus V sub A, that potential difference between those 2 points is equal to 0. Another property that we've already mentioned with ideal wires is they have 0 resistance to electric current. So if we take an ideal wire and look at the charges flowing through that ideal wire, we would see that those charges would move easily without resistance to its movement. Now, that's in contrast to what we presented earlier, in which here, this wire is definitely not ideal because the charge is moving through, and when I say this wire, I mean this one that I'm highlighting right here. How about this one that I'm highlighting? Let's try that again. This one that I just highlighted. This is not an ideal wire because the charges moving through this wire encounters resistance, which influences its rate of flow. However, we could consider this segment to be an ideal wire, no resistance of movement, and this segment can be considered an ideal wire, no resistance to movement. Another property of an ideal wire is the current is the same at all points. So current is the movement of charge, and you can think of it as the rate in which charge moves across a cross-sectional area. So let's just do another picture. Let's say we have an ideal wire, and I'm exaggerating the size. And let's say we're looking at the charges flowing through this ideal wire. We want to measure the current, and we want to measure the current at a particular point in this ideal wire. So we'll measure the current as these charges cross this cross section of the wire. So the thing about ideal wires is the rate at which current is flowing is the same at all points. Let's look at this negative charge, and let's measure the current, the rate at which negative charges move in this wire at two different points. We will call the point on the left point A and the point on the right point B. Well, the rate at which this charge moves across point A is the same is the same rate as it is when it moves across point B. And we don't have to just have the single charge. We could have multiple charges. And the rate in which these multiple charges move across the 2 points is the same. So the movement of charge is the same at all points in an ideal wire. In other words, the current is constant everywhere in an ideal current carrying wire.